Hi guys, so we're going to go over and try some of these Lewis dot structures and VSEPR structures and determine their electron pair geometry and molecular geometry. So let's get started. So the first thing that we have here is nitrogen trichloride. There's one nitrogen and three chlorine atoms. So we're going to find those on the periodic table first. So the nitrogen you can see is right there and the chlorine is right there. And so what I generally do then is figure out how many valence electrons. You can do the long electron configuration to figure this out, or you can remember that we had 1A, 2A, come over here 3A, 4A, 5A, 6A, and 7A. And so those numbers tell us how many valence electrons we have. So the nitrogen is on the fifth, and so that one's going to be 5. So I'm going to write that over here just to begin with so that I know what their Lewis dot structures look like for the individual atoms. So we have 1, each side gets a dot, and then so that's 4, and then there's going to be 2 pairs that actually come together here. Now chlorine is where there is 7, and so we have 1, 2, 3, 4, 5, 6, and 7. So if you look at this, you'll realize that these guys basically have the capability of bonding here, and bonding here. So there's 3 chances for it to bond. This guy can only bond here, so there's 1. So this would be our central atom because there's more capabilities of bonding. Now, if you remember, we don't have just 1 chlorine, we have 3. So this is going to be 3 of them. And if you look, there are 3 spots here that there could be bonds. So let's go over here and write our Lewis structure. We're going to start with the N in the middle, and we're going to write them like that. And then because we have 3 chlorine, let me put that L there, sorry about that. We're going to write those next to it. So with the lone electron going towards the actual atom that we are going to bond it with. And so you can see at this point that there are electron pairs right here. Now we can write that as a single line will indicate that there's a bond. And so once we get that done, there's a couple things we want to do next. The first is we want to figure out what the electron pair geometry, and what is that saying? It's just saying where are their electron pairs? And from there we can figure out where those electrons are in 3 dimensions. And so if you look, we have a pair here, a pair here, a pair here, and a pair here. So there's 4. And that shape is what's known as tetrahedral. And you'll notice that the tetra is there for 4. The next thing that we're going to do is the molecular geometry. We're going to ask, what is the actual shape of the molecule? So there we're just contemplating essentially where the atoms are in 3 dimensions. Now I want to note that where the non-bonding electrons or these electron pairs, i.e. those guys, those dictate the shape. Those are going to be at the top, and because there's a lot of negative charge, it's going to kind of repulse the other 3 bonds that are around them. So essentially what you're going to get here is 3 bonds that are in the shape of what looks like a little pyramid. And so that's what's known as a trigonal pyramidal. Now from your handout, you'll be able to figure out the VSEPR structure is basically taking into effect the 3 dimensions with the electron pairs. And so basically what that looks like is this. So we have our 3 Cl's and then our electron pair up here. Now these guys represent the plane of the paper. This is coming out and this is going behind. And so that's our answer. And just to let you know, we're not going to actually hit on these during this video. So that's our first one. Now we can check this. And how you check this is essentially looking, and unfortunately it's going to erase what we've done here. But we can go here. And how you use this is you go for what the central atom is. And so our central atom was nitrogen and it had 5 valence electrons, so you go here. And if you realize we had 4 electron pairs, those are the actual electron pairs, right? 3 sets that were actually bonding, so those are the lines between the molecules, or between the atoms. There was 1 that had a non-bonding set of electrons, and that made R-shaped tetrahedral and trigonal pyramidal. So this is what you can use to test it. And this is the last time that I'll be kind of going over what this is. You can check these on your own to make sure that you got them right essentially later. And so I'm going to pull this into the back now. And we are going to move on to our next guy, which is potassium iodine. And I'm going to move this down so we can see where those are. So again, we want to see where they are. Potassium is here. Iodine is here. Now there should be a big red flag that goes off right now. When we're looking at nitrogen here and chlorine here, they were both considered nonmetals, which means they form covalent bonds. And from covalent bonds, we can get VSEPR or 3-dimensional structure because they actually form a molecule with a very specific shape because of where those covalent bonds are located. Now, if we look here, we have potassium and we have iodine. This is a metal and this is a nonmetal, which means that these guys are an ionic bond. And so with this guy, we're going to do again our Lewis dot structure. So potassium has 1, iodine has 7. And how do I know this again? This is our 1A and it goes down from there, so that's 1. This guy is our 7A and goes down there as 7. Now, if we know anything about potassium iodine, we know that essentially when we are looking at this, that the potassium is going to get rid of its electron to essentially become more stable in its form of its noble gas. So then that's going to make potassium positive because it gets rid of it. The iodine is going to be negative, and that gives us the Lewis structure for potassium iodine. We won't have a Lewis structure, and we won't have any geometry for this because it's an ionic bond. Let's move on. Move this up a little bit. And let's go here. So we have dichloromethane. So we have a carbon. We have a hydrogen. And we have a chlorine. So the carbon is 4. The hydrogen is 1. And we have 2 of those. And the chlorine, again, is 7. And we have 2 of those. So, of course, this is going to be our central atom because it has the most. We can bond with 4 things here, where these guys we can only bond with 1. So we're going to come over here. We're going to write our Lewis dot structure for chlorine, and then we're going to put our atoms accordingly around it. Now realize you have to put all the dots around chlorine. You cannot just write chlorine down without the dots. That's incorrect for this. And we can put the lines here to indicate that we have bonds between the two atoms. Now the electron geometry here, well, we have bonding electrons here, here, and here. So there's 4, so we have tetrahedral. On this guy, we have how many are actually in bonds? 1, 2, 3, and 4. So again, we have tetrahedral. And when we go to do the VSEPR structure for this guy, it's going to look like this again. It's going to have an H, an H, a Cl, and a Cl. Again, we are not going to address the AE or ABN designations. So now let's go on to the next one. Magnesium bromide. So when we go, let's go, we have magnesium here, bromine here. What do we notice, guys? It is. So when we have this, magnesium is going to have 2, and the bromine is again 7. And it is a ionic bond. I'm doing this so that you guys realize that this is for things that form covalent bonds. And so magnesium will be our center, right? And what's going to happen is these guys, he's going to have all of them around, and he's going to be negative, right? And this person, I think I've gone a little crazy, guys, is going to basically have magnesium as +2 because magnesium is going to give 1 to each bromine. And so these guys will work together again. Because it's ionic, it will not have electron pair geometry, molecular geometry, or the VSEPR structure. Let's move on. Sulphur difluoride. So let me move him down a little bit. Move on. And let's do this. So we have sulfur here and fluorine here. So sulfur is going to be 7, or 6, sorry, because it's the 6A group. And fluorine is going to be 7. So these guys can form 2 bonds, where he can form 1. So the sulfur is going to be my central atom. And then I have 2 fluorines. So we're going to draw the line between the 2 again because they form bonds. And the first thing we're going to do is electron pair geometry. We look, how many electrons pairs do we have? We have 1, 2, 3, and 4. So he is going to be tetrahedral. The next we're looking at is how many atoms do we have bound? And we have 1 and 2 here. So when we have 2, it's going to give this look like we talked about in water that is bent. These are going to bend down, and essentially the on-bond electrons are going to be at the top. So what you're going to end up seeing here is essentially what looks like this. So let's move on to the next one. Hopefully you're starting to figure these out a little bit and realizing that some of this is memorization. Carbon dioxide, carbon and oxygen here. So carbon is 1, 2, 3, 4. Oxygen 1, 2. 3, 4, 5, and 6. So you should be figuring out now that this guy can do 4 and this guy can do 2, and there's times 2 of these. So carbon is going to be your centralized atom. So you're going to write this 1, 2, 3, 4. And then you'll write oxygen next to it. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now, what I would say for you guys to do is look. Because if you look at this guy, you'll notice that this guy can form a bond with this guy. And this guy can form a bond with this guy. But if you notice, we have something up here and we have something over here. So this is when we're going to start forming things called double bonds. And this is where you would look at the what we had on the next page. It says molecular geometry of compounds with double and triple bonds. And so this is the next table. And basically what's going to happen is he can form a bond with him and he can form a bond with him. And so what you end up getting here, guys, is something that looks like this. And so you have where you get 2 bonds between carbon and the oxygens. And so when we look at this, you'll go and you can find in your thing, you go, how many valence electrons does my central guy have? Well, he has 4. How many electron pairs does he have total? 4. And then you ask him, how many is he bonding with? Well, all 4. So there's none left. Then you ask yourself, how many double bonds does he have? Well, he has 2 double bonds. So that means he's going to be, for his electron geometry, is going to be linear. Basically, all his stuff is here and here. So it's in a straight line. And the bonds he makes are here and here in a straight line again. So it's linear. So when you draw this out, it's going to look linear. So the VSEPR structure is the same as the Lewis dot structure. Good job. Let's move on and go to the next one. Anhydrous aluminum chloride. Now this guy's a little weird. You'll notice that I have a special word next to him. So when he's in his crystalline form and he's not in water, aluminum is, if you look over here, and then this is right here. So due to the electronegativity and due to the size of chlorine, this guy, if it's not in water, is going to form a covalent bond. It's kind of weird. You would think aluminum, it's metal. It's because of the location of where they are on the periodic table. And so this guy is a little bit different. So we're going to write him down. This is 1, 2, and 3, right? So he's going to have the 3 valence electrons. 2, 3. And then the chlorine is going to have 7. So that should tell you what your central atom is, the aluminum. And so what you're going to do over here is and you have, just to remember, 3 of these. So that'll fit perfect with this. So he's in the middle, 1, 2, and 3. Or actually, let me take this from the top and just put it on the bottom. There's more room. So 1 here, 1 here, and 1 here. And remember, we can make these lines here so that you can basically see how all of this works. And now we're going to look at the famous, which we've been doing, electron pair geometry. There's 1 here, 1 here, 1 here. There is not 1 up here, okay? So this, we have 3, and we have 3. It is considered what? Trigonal planar. The reason being, there's 3 of them, so it's almost like a triangle, but it's a triangle that if you squished it out and it was all in the same plane. There's normally what we have up here is if we have electrons up there, it forces them down into an actual pyramid. That's when you hear words like trigonal, pyramidal, which actually makes a pyramid shape, where this is trigonal 3 planar, which is squished straight on a plane. And as you can see here as well, guys, is you have atom, atom, and atom. And so the molecular geometry is the same. So if you look at your handout, what would it look like? Well, it would be it would look like this. We are halfway through, so hopefully you're getting a little bit better with these. So we're going to do hydrogen iodine. If you see, iodine is down here, which makes it 7. I'll move that back up. So iodine, oops. Is 7, 1, 2, 3, 4, 5, 6, 7, and hydrogen is 1. So essentially when we're looking at this, it just does this one bond right here between each other. And so when you have these single just bonded together, we can go and this we're going to focus on the hydrogen. We're focusing on the hydrogen because if you look at what we can do right here, electron pair totals are 4 and bonding. So these, we're going to do them for two things. So on here, if we're looking at the hydrogen, it would be 1, right? There'd be 0 non-bonding. And so something like this, you would look and it would be, if you're looking at something like this, you would be looking at something like H2. And both of these are the same. So in this case, it would be linear and linear. If you were looking at the iodine, it'd be a little bit different, right? The electron pair geometry, well, we'd say that it would be 1, 2, 3, you'd have 4. So this would be tetrahedral, and the molecular would be only 1, so it would be linear. And to make this guy really easy, it's linear, so it would only look like that. So I'd accept either one of these answers if you were going through it, unless I specified which one I wanted from you. We're on our 9th, and we have methylamine. So from here, we have C, we have H, and we have N. So our C1, 2, 3, 4. Our N, 1, 2, 3, 4, 5. And our H is 1. Now the thing you should look is, in this molecule, you'll notice that this N is attached and then it has the H's. So they're telling you that 2 of these bonds here have H's in them. So that's going to reduce this to having 1 ability to bond. This has 1 ability and this has 4. So that should give you an idea better of how you would set this up. So carbon would be your centralized atom. Even without knowing that, nitrogen only has 3, but you can look at how your formula is set up to figure out where things are bound. And so essentially you have 3 H's bound to the carbon, and then the N. And essentially from this, you have a pair of non-bonded, and then the 2 hydrogens. Now when we do the electron pair geometry, we're doing it for carbon. So we have 1, 2, 3, 4. That's tetrahedral. We have 1, 2, 3, and this whole thing is considered 4. Again, it's tetrahedral. And when we go to write the VSEPR structure for this guy, we're going to put C in the middle. You can do the NH2 at the top, the H off to the side, and the other H's here. So that gives you the actual VSEPR three-dimensional model. So don't get tripped up by these things that show you a bigger molecule in there or give you a couple atoms that tend to have a lot of binding capability. Look at how they're arranged in the actual the formula. Let's move on to the next one. Hopefully you're having fun. Lithium selenide. So lithium can be found right here. And the selenium is found over here. So 1, 2, 3, 4, 5, 6. So you write these like this. And you should notice one thing right off the bat since you're looking at the periodic table. Ionic. So you get really happy because you don't have to write all this other stuff, right? So essentially when we look at this guy it looks like this. But basically what's going to happen is the lithium is going to give its electrons to the selenium. And so then we're going to get the 2 or 2 minus here, and then each one of these is going to be a positive. And so just wanted to throw another one of those in there so that you know when you're going through these that these guys are ionic and will not be, basically, you won't have to do all these things because they don't have a defined molecular shape due to the covalent bonds, which is what VSEPR is showing us. Oxygen. Can't do anything without oxygen, and oxygen just likes to interact with everything and everybody. So oxygen is here as 6 valence electrons. There's 2 of them. So if you remember earlier, these guys will bond, and then these guys will bond, forming this structure here. So this is when you go where it has the single bond, the double bonds, and you say, how much does this baby have? Well, he had 6 valence electrons, total electron pairs. He's 1, 2, 3, 4. Electrons that are binding are 2. He has 2 non-pairs. He has basically 1 double bond. And so what he is his electron pair geometry is 1, 2, and 3. So he is trigonal, planar. And if you look, they are right across from each other in a straight line, so he is linear. And so when you go to draw this structure out, they're straight from each other. We're on number 12 now. I really hope you're getting these going through here. We have hydrogen and carbon. Carbon again, 1, 2, 3, 4. Hydrogen, 1. We have 2 carbons and 2 hydrogens. So we're going to draw our carbons next to each other because they both have the capability of making 4 bonds, where hydrogen can only make 1 bond. So we'll put the hydrogens out next to it. And we're done with the hydrogens, and you'll notice that this guy forms a bond here. And then essentially we have these left over. So he can form a bond with him. He can form a bond with him. And then you get triple bond acetylene. And so if you look at the double bonds, right, you can pick either one. It's the same on both sides. You'll see that you have 4 valence electrons, 4 binding pair. You have 4 that are in actual bonds with each other. It says how many electron pairs that are non-binding. It's 0. Double bonds, no, we don't have 1 double bond. We don't have 2 double bonds. We have a triple bond. So that's going to make the electron pair geometry linear. But you can see they're all right here, right? They're all in a line together. And this is bound here with this. So this guy's going to be linear as well. Actually, and then if we're going to draw the VSEPR structure for this, it's just in one long line. So close to being done, we have 3 left. Phosphorus trichloride. So we want phosphorus here, chlorine here. So this is 2, 3, 4. Wait, 3, sorry, 4, and 5. 2, 3, 4, and 5. And chlorine is 7. So this guy has 3 capability to making bonds. This is only 1. So the circled is going to be our centralized atom, and realize there's 3 times of these. So we're going to write this. And T is going to be bond. I'm going to write these a little bit faster since I feel like we should be getting to the point of understanding this. Now we're going to do our electron pair geometry. Well, we have 1, 2, 3, 4 tetrahedral. And we have 1, 2, 3. We have 3 of these down at the bottom, and remember, we have the unbonded electrons. So that's going to push them down into that pyramid shape that we know as trigonal pyramidal. Now the last thing we want to know is the VSEPR structure, which is the electron pair geometry. So we're going to do this guy, which it looks a lot like the aluminum chloride that we had earlier. And we have 2 left. Ammonium ion. So we have a nitrogen and a hydrogen. So we have 3 here, and the hydrogen is 1. Of course, this is 4 times, and we have 3 bonds that can be formed with that guy. So nitrogen is our central. So we come over here. Oops, let me erase that. He looked bad. 1, 2, 3, 4, 5. And we have a hydrogen here, a hydrogen here, and a hydrogen here. And we're like, wait a minute. We're going to put a hydrogen here. There can't be 3 there. No, no, no. Can't be 3. So we're going to get rid of him, which will put us, if we get rid of one of our negatives, it's going to make us positive. Now we look here. How many do we have for electrons? 1, 2, 3, 4. So we have tetrahedral. How many bonds do we have? 1, 2, 3, 4. So we have tetrahedral. And when we draw him, and we're just going to put it on the outside so everybody knows that he is positive. And the last guy we have is bisulfite ion. So we have here a sulfur and a hydrogen. So let's write their their Lewis dot structure. This is 3, 4, 5, 6. And the hydrogen is 1, and we have 2 of these. So we have 1 of those. So we know that this one has the capability of making 2 bonds, so he's going to be the center. And then we have hydrogen here for 1. Well, the thing is that he is not stable because he is not completely bonded. He doesn't have his whole octet. So we're going to add an electron here, and that is going to, since we're adding a negative charge, he's going to be negative. Now we look at our centralized atom, which is the one that can form the most bonds, which is him, right? And so when we go, we do 1, 2, 3, and 4. So it's tetrahedral, but he's only bound to one thing. So it's linear. When we do this guy, you'll have all your unbounded electrons there. So guys, we're done. So hopefully that helped. If you need any help with actually the modeling of anything, just come into my office and I will be very happy to help you and put some models together so you can see things. Thank you.